Okay, good afternoon, everyone. My name is Chulukushadisi. Today, I'm going to take you through a tutorial on how to solve physics problems. In particular, we are going to attempt questions from tutorial sheet 1, which deals with kinematics in one dimension. Okay, so in this tutorial, basically, what I want to teach you is basically how we go about solving physics problems, which I usually call the physics way of solving problems. So in physics, when you are faced with a problem, the first thing that you do is basically to make sure that you work out all the physics, you solve all the equations, and at the very end, that's when you want to substitute the values. So that's just basically what I want to demonstrate to you in this online tutorial. Okay, so here we have a problem. We have a question which reads: on your wedding day, you leave for church 30 minutes before the ceremony is to begin, which should be plenty of time. Since the church is only 10 miles away. On the way, however, you have to make an anticipated stopover for construction work on the road. As a result, your average speed for the first 15 minutes is only 5 miles per hour. I think here there is a typo. This must be 5 miles per hour. What average speed do you need for the rest of the trip to get you to the church on time? So here we have a situation where you're coming from home probably, and then you want to go to church for some wedding ceremony. And then on the first part of the trip, because there are some works that are going, construction works that are going on the road, you can't drive so fast in such a way that you can only drive at an average speed of 5 miles per hour. And this is for the first 15 minutes of the trip. Okay, so on the second part of the trip, so the question is that what should be the average speed? What should be the average speed at which you should drive so that you make it for the wedding ceremony in time? So when you're faced with such a problem in physics, the first thing that you want to do is to construct a coordinate system. So this is my y-axis, and this is my x-axis, so that we picture clearly what the question requires of us. So here we are saying that we are going to take the origin as the point where the motion is starting from. So in this case, if you want, it is your home. So this is your home, where you're coming from. And then ideally, you want to get at this point. On the x-axis, we have assumed that this motion is taking place along the x-axis. So this is the church. This is the church where you want to go. So basically, we see that we can divide this trip into two parts. We can divide this trip into parts. The first part, we can call it x1. So we can say from here up to here, we call it x1. Just the first part of the trip. And then during this part of the trip, you're actually moving slower because there's congestion on the way. And then let us call this other part of the trip as the x2. This is the part where now you don't have congestion, and you have to make sure that you drive at a speed that will allow you to reach the church in good time. Okay, so what we are saying is that this point where you're starting from is your initial point. Remember, the initial point, we are calling it the initial position. We are calling it x0. The other thing that we have to do on the diagram is that we have, the time that it takes for you to move from home up to this point where the congestion ends. Let us call it T1. Call it T1, and the time that it takes for this point up to the point where you get to church, let us call it T2. All right, so from these equations already, maybe let us say that the distance from home, this distance from home up to church, this distance, we call it X. It's the total distance that has been moved. So just from what we have done so far, I think we can already find some relationships. You can find these equations. You can see that the total distance that you move from home up to church, this X, will just be equal to X1. From the diagram, you can see that is equal to X1 plus X1 plus X2. So this one is our first equation. This is the relationship, because the total distance that we have moved is just basically the distance that you moved in the first part and the distance that you moved in the second part. The other relationship that you can find is that the total time taken on the trip is simply a sum of the time taken on the first portion of the motion, which we have called T1, and the time taken on the second portion of the motion, which we have called T2. So this becomes our first equation. So already we see that we are having some equations. All right. So now let us move on the next. Let me make some space here. So the question that we are looking at basically is this one. So the question that we're looking at. So let us now try to look at the data that we have. So this is the data that we have. So I read the question again. On your way, on your wedding day, you leave for the church 30 minutes before the ceremony. So it means that you have 30 minutes for you to reach the church so that you attend that service. So if you have to go back to this, it means that this T, the total time already, we have established that it is 30 minutes. So that will be part of my data. So I go there, I say that the total time is basically 30 minutes. Okay, now if you look carefully, since the velocity has been given in terms of miles, per hour, so I want to convert this into hours. I want to convert this minutes into hours so that it becomes convenient for me. I know by this time, I'm sure you guys know how to do that. I will not go through that, but 30 minutes is basically 0.5 hours. Basically, it's half an hour. So that is that. And then what is the other piece of information that I have? Okay, so on your wedding day, you leave for church. For the church, 30 minutes before the ceremony is to begin, which should be plenty of time since the church is only 10 miles away. So what is this 10 miles that has been given here? This 10 miles is the total distance that is from home here up to the church. So this is basically the X. So this X, the total X is I've seen that it is 10 miles. X is 10.0 miles. Okay, and then on the way, however, you have to make an anticipated stop for construction work on the road. As a result, your average speed for the first 15 minutes. Now I have this piece of information here again. The first 15 minutes. So this represents, if I have to go back to that diagram, then this basically just represents the time that it takes. It represents T1, the time that you take in the first part of the motion. So I also know that this T1 T1 is nothing but 15 minutes, which I can convert to hours in a similar way that I did to the T. So if you do that, then you see it will be 0.25 hours. 0.25 hours. That's our T1. And then your average speed for the first 15 minutes is only 5 miles per hour. 5 miles per hour. So this is the average speed. So I'll say that this the average speed for the first part. Remember, this is the first part of the motion. This bar, this thing that I put, the bar, it just represents average. So the average speed is basically just 5.0 miles per hour. Okay, so this is the data that I have. And what am I looking for? These are the known quantities. And what am I looking for? I'm actually looking for the average. What is average speed during the second part of the motion? So I'm looking for this average speed in the second part of the motion. So this I don't know. And then what are some of the things? Let us look at the diagram. Some of the things that you don't know are also x1, the distance that was covered in the first part of the motion. That one we are not given. And then also the distance that was covered in the second part of the motion, we are not given. The only thing that we know is this relationship that exists here. So in short, we are saying that this x1 is also not known. The x2 is also not known. Okay, so now what strategy are we going to use in order for us to find it, to solve this problem? So the strategy that we may use, you can see that here we have the average velocity here. By the way, I must mention that I'm not bothering to change these miles per hour into probably kilometers per second or whatever units that you want, because I know that these units are consistent because the time has been given in hours. Okay, so I know that these hours will cancel out, and also the miles will cancel out because you see that the distance has been given in terms of miles. So I don't need to convert anything in this particular case because the units will eventually cancel out. So the first thing that I want to do is basically to find the formula for average velocity. What is the formula for average velocity? So I'm going to say from average velocity, remember average velocity is just equal to the displacement that has been covered. The displacement, remember, is the final velocity minus the initial velocity. So this the V1, if you want, the average velocity in the first part of the motion can be given as, let me just go back a little bit on my diagram. So I'm saying that on the first part of the motion, there you are actually moving with a velocity, an average velocity of V1. So this V1, if you can remember from the chapter 1, from the chapter 2 that we learned, it is basically the displacement taken, which is the final position minus the initial position over the time that has been taken. So we are saying that average velocity is basically the final position. In this case, the final position is x1 minus the initial position, which is x0, where the motion was starting off from. And then over the time taken, remember the time taken is t1. I'll just go through again for the sake of clarity. You see, on this first part of the motion, the displacement that has been made is the final position, which we know is x1. Here is x1. Then the initial position here is the x0. So the difference between these two gives you the displacement. And then if you divide the displacement over time, then you find the average velocity. Okay, so this is where this equation has come from. So as usual, let us try to substitute the zeros the zeros from this equation, you know that this value is equal to 0 because we have assumed that the motion is, the home is coinciding with the origin where x naught is equal to 0. So from there, then this will just imply that the average velocity for the first part will be equal to this x1, which is the displacement covered, and over t1. And this implies that this x1, remember x1 was one of the things that we didn't know here. So now I'm sure we'll be able to tell because this is just equal to v1 times t1. Okay, so I have another equation here. You see, I can call it equation 3. Now, if you look at this equation, I already know my V1, it has been given, it is 5 miles per hour. And I also know the T1 that has been given is basically nothing but 0.25 hours. Okay, so actually I can find out what my x1, which is the distance that is traveled in the first part. Okay, I can put the values, but for now I don't want to do that. If you want, it will still not hurt to put the numbers so that you find a numerical answer. But for me as a physicist, I just want to leave it at this particular point, and then I'll come and substitute all the values at the final, in the final analysis. All right, so let us now proceed and see. Just allow me to create this again, so that okay. So the question I want to be looking at the question. All right. So from the previous slide here, you see I have found my x1. I have found my x1. Now, what is the relationship between this x1 and this and the x2? What is the relationship? So I know from my equation 1. Remember equation 1 here, it tells me that x is basically equal to x1 plus x2. So let me try to use that piece of information to see what I can do with it. So from equation 1, I know that x is just equal to x1 plus x2. So since I know my x, I also know my x1 from equation 3. Then let me make x2 subject of the formula. x2 will just be equal to x minus x1. Okay, so x2 will just be equal to x minus x1. But remember x1 was just nothing but the average velocity v1 and t1. This is just coming from this equation here. X1 was given by that. So where there is x1 here, I want to substitute this. So x2 will just be equal to x minus x1, which is v1 and t1. Okay, so I'm making progress here. Now let me try to inspect. If you look at x2, I think I already know my x. The x, remember, it is nothing but 10 miles. X is 10 miles. And what else? I know my v1. Remember, v1 is nothing but 5 miles per hour. And I also know my t1, because t1, if I want, I also know my t1, which is 0.25 hours. So even at this particular point, this equation, if I can call it equation 4, from equation 4, if I want, I can substitute all these numbers so that I come up with this x2. Okay, but as a physicist, I don't want to do that because I want to substitute the numbers at the very end. All right, so what do? I just save that as my equation, 4. Okay, so now again, what is the average velocity for the second part of, I'm now considering the second part of the motion from here up to here. I want to find what then is the average velocity. This is what the question is asking for. So when I consider the second part of the motion, I know that the average velocity for the second part will just be given by the displacement that has been covered. Remember, the displacement that has been covered in this particular case, if you look at it carefully, it will just be nothing but the total distance here, which is x, the total distance minus this x1. Okay, so this is just what has been covered here. So I will say V2 is the total distance that has been covered, which is x minus x1, okay, over the time that has been taken, which is t2. All right, so if you look at the numerator, this x minus this numerator here is just nothing but the x2. If you look at it very carefully from the diagram, this entire thing is just nothing but x2. So the V2 will just be equal to x2 over t2 in short. But then what am I looking for? So I'm saying that this V2, which is the average velocity for the second part, can just be given as x2 over t2. Now look at this equation 4. From equation 4, this x2 here, I can just write it as x minus v1 and then times t1 over t2. All right. Okay, so this v2 can just be written as x minus v1. You see, this is just I'm just substituting that value there. That's basically what I have done. And now let me just write it properly. So again, I want to create my question so that I'm looking at it. So let me just write this V2. Okay, so I'm saying the average V2 is equal to, what did I have? X minus V1 T1 over T2. So let me see. This V2 is actually what I'm looking for. Now, what do I have? I have X is, by the way, I must mention this here. You can see is basically my answer. This is what I call the symbolic answer. Because if you look at this, you have all the parameters in this equation. I think you have X, you also have V1, you also have T1, and T2 you can also find it. So this is basically the symbolic answer. What I'm just remaining with is to push in the values, just to substitute the values. So the data, remember, looks like this. X was the total distance was just nothing but 10.0 miles. And then V1, the average velocity, I think we had found that it was 5.0 miles per hour. And then what else are you looking for? You're looking for T1. T1, we had actually computed T1. If you remember very, very well, we found that it was 0.25 hours. And then T2, how are we going to compute T2? You remember from that equation, which says that T, the total time, is just equal to T1 plus T2. So that equation implies that T2 is just equal to T minus T1. Okay, so the T2 will just be equal to, you see, what was my total time? The total time, as we said, was 0.5 hours. The total time, it was 30 minutes, remember, and we converted it. And then minus What is T1? T1, we had found it to be 0.25. So if you compute this, then you just find that T1 is also 0.25 hours. Okay, so you see that you have everything now that you have. You have the numerical values for all the parameters. What you just remaining with is to substitute there in the answer, in the symbolic answer. Okay, so let us try to do that. So remember the equation that I have is V2 was equal to V2 is equal to x minus V1 T1 over T2. So I just have to now substitute the values. V2 will just be equal to x. Remember, x was 10.0 miles. And then what was V1? V1 was 5.0 miles per hour. So I must actually multiply this with the time, which is 0.25 hours. I multiply with this with the time, and then over everything over T2, which is 0.25 hours. All right, so you can already see how the units are canceling out. This cancels with that. So in the numerator, the units that you are just going to have are units of miles. And then, of course, in the denominator, the units that you have are hours. So you can already see that the units are consistent with the velocity. So now this is just remaining with the calculator. You must now use your calculator. You punch these numbers, and then you be able to find. No, just try it out. Give it a try. Then you have 8.75 miles per hour. All right, so now 0.85 miles per hour. So you want to express this to the least number of significant figures. The least number of significant figures in this calculation, you see, this one is the one that has got the least significant figures, as well as this one. So you have to correct this to two significant figures. Then V2 will be nothing but 8.8 miles per hour. So this is your answer. And what does it mean? What it means is this, that if you are coming from home, this is your home, and then here there was too much congestion and you were just able to move at a low speed of 5 miles per hour. And then here, since here you have little time remaining, it means that you have to increase the speed to an average of 8 miles per hour if you are to make it in time for the church service. So basically, this is how you are supposed to work out this problem. And the emphasis here is, you see, I first concentrated on the physics of the problem, trying to see the relationships between the parameters that I have. I modeled the question by way of drawing a diagram on the coordinate system. By the way, I should have written that. Okay, so I modeled my problem. I wrote a diagram which helped me to solve the question. And then throughout the question, I made sure that I was only dealing with symbols, and then until I arrived at the symbolic answer. It is in this symbolic answer that now I plug in all these values, and until I now reach the numerical answer. So in short, that is how you work out physics problems. All right, so let us try one more problem. A car and a truck are heading directly towards one another. This is important. On a straight and narrow street, but they avoid a head-on collision by simultaneously applying their brakes at t is equal to 0. The resulting velocity versus time graphs are shown in the figure below. So here I have no figure, but very shortly, I think you have the figure in your Excel sheet, and I'll also show you very shortly. Okay, so the question is that, what is the separation between the car and the truck when they have come to rest, given that at t is equal to 0, at t is equal to 0, that is the initial time, the car is at x equals 15 meters, and the truck is at x equals minus 35 meters. Okay, note that this information determines which line on the graph corresponds to which vehicle. So before we go to that, let us try to picture the problem by way of drawing the situation. So this is my coordinate system. So that is my y-axis. And then here, this is my x-axis. So this is my x-axis. You see that in this case, my entire motion is taking place along the x-axis. So this y-axis is even almost redundant. So according to this data that have been given, at t equals 0, the car is at 15, at the position 15 meters. So the car is at a position 15 meters. Let me just say this is the position 15 meters. I will not write the number, so I'll just write this is the initial position of the car. So this is the x naught for the car. And then the truck is at minus 35 meters. So minus is on this other side. This diagram, remember, is not to scale. So the truck, the initial position of the truck. So in this case, I'm saying that T represents the truck. So everything that will have a subscript of T will be for the truck. And then C represents the car, because everything that has a subscript of C will be for the car. Okay, so since we are saying that the car and the truck are headed in, they are headed directly towards each other, it simply means that this car is moving in this direction, and I'll call this as the initial velocity of the truck. Sorry, this is the truck, the initial velocity of the truck, and the car is also moving in this direction, and I'll call this as the initial velocity of the car. Okay, so it is only in this situation that the two can head directly towards each other, so that there will be this head-on collision. Okay, so now this is at the time t is equal to 0. Now, what does the question require? What does the question require? The question requires what? The separation distance. What is the separation between the car and the truck when they have come to rest? So maybe let us try to define certain things. So we'll say let xt be the final position after it has stopped. What was the final position of the truck? The final position of the truck, and let xc be the final position of the car. Okay, so I have defined those two things. Xt to be the final position of the truck. You see the truck is moving in this direction. And then xc, it will be the final position of the car. You see the car is moving in this direction. Okay, so now I have tried to picture my situation, the problem that I have. And then now let me try to write the knowns and the unknowns. Let me try to present my data. So I create myself some text. I always want to be seeing my question. Okay, so it seems I'll not be able to do the question. Let me just, I'll be going to it from time to time. So let me try to write out the data that we have. Okay, so since we are saying that what do we know about the problem? So we are saying that this x naught, the x naught, the x naught c, the initial position of the car has been given as 15. The initial position of the truck has also been given as minus 35 meters. Okay, so I go there, I say the initial position of the car is 15 meters, and then the initial velocity of the truck is minus 35 meters. Okay, so I'm sure that is there. That is the data that we have. And then what else has been given? What else has been given? All right, do we have the initial velocities? Do we have the initial velocity of the truck and the initial velocity of the car? So let us go to the diagram. Let me share the diagram with you. Okay, so let us go to the diagram so that we see whether we have this. Okay, so you see, this is the diagram that I have. And then now I have these two lines. I have these two lines. There's this one line that is here, and there's this also the other graph that is here. So how do I identify which one is for the car and which one is for the truck? How do I identify which one is for the car and which one is for the truck? So we know that the car was initially, if you look at that diagram very well, I draw it again. If you look at it, this is your origin. The car was on this side, so its velocity was this side. So if you take this as your positive x, then the initial velocity of the car should be negative because it is in this direction. So the initial velocity of the car should be negative. And then since the truck was this side and it was moving this side, we say that the initial velocity of the truck was in that direction. You see, it's along the positive x-axis, so it is actually positive. So from the graph here, you see that the initial velocity of the car should be negative. So since this is the graph that has got an initial, see at the, you see when the time is 0, the initial velocity is negative. So this should actually correspond to the car. Why? Because the car has got a negative velocity initially. And this should correspond to the truck. Why? Because you see the truck has got a positive velocity initially. Okay, so having identified that, then I can even identify now, since I've said this is for the car, so this was the initial velocity for the car. So it means that my V naught for the car, the V naught for the car was minus 15.0 meters per second. Similarly, my V naught for the truck was nothing but 10 meters per second, which is a positive. Okay, so just there, we have the information from the graph. The other thing that we want to find from the graph is the the distance traveled. You see, at just after the point where this guy starts slowing down, see the velocity is reducing. You know that the area under the curve represents the distance that was traveled. So how do you calculate the area under the curve? The area under the curve is just half of the base times height. So this area here just represents the distance that was actually moved by the truck as it was slowing down. And this area that is here it represents the distance that was moved by the car as it was slowing down. Are we together then? Okay, so let us try it now to compute. Let me now go back to my, so let us just have these values. Let us just try to have these values in mind of what we have gotten, the initial velocity. The initial velocity for the car was minus 15.0, and then the initial velocity for the truck was 10 meters per second. Okay, so let me now go to my go to my board. I want to go to the board so that I pick it up from where I had left. So what do I know? So for now, by now I have established that V naught C is nothing but V naught C is nothing but minus 15.0 meters per second, and then V naught T is nothing but 10 meters. Actually, it should be 10.0. I just want to be careful with the, so 10.0 meters per second. All right, so what are the unknowns? What are the unknowns? What I want is the separation. I want the separation distance. I want the separation distance after the two have stopped. After the two have stopped. So let me call this separation distance. Let me just call it delta x, the separation distance after the two have stopped. Now, what is this separation distance? Basically, in form of an equation, this separation distance, it will just be the final position of the car minus the final position of the truck. So basically what we are saying is this truck is moving in this direction, this car is moving in this direction, and both of them are braking. So it means that the separation distance after they have stopped will just be the final position for the car minus the final position for the truck. If you do that difference, then you find it. So if the car is coming here, and then if it stops here, then the truck is also coming here, maybe for argument's sake, it stops here. Then the separation distance is just this guy here, minus this guy here. Then you have found the separation distance that you are looking for, and that's what we have called delta x. So the final position of the truck is this, the final position of the car is this. So that's where this equation has come from. That's where this equation has come from. Let me try to number it. I say that is my equation 1. That's my equation 1. Now, from what we had discussed, we say that I can find the distance that the truck has covered when stopping. So I call this as the delta t, the distance that the truck, sorry, I think I have to rub this. The distance that the truck has covered, the distance that the truck has covered. Okay, so I'll call it stopping distance. Stopping distance of truck. And then this one, I'll call it the stopping distance of the car. So I have this notation. So now what is the stopping distance? What is the distance that the truck has covered when stopping? So we say that it is just the area under that graph that we are given. So you know that the area is just half base times height. So to make it easier for you guys, let me just put the numbers. So there you can see the half. If you look at that graph very carefully, the base is about 2.5 seconds, and then the height is about 10 seconds. Just try to go to the graph and confirm this. So this gives you 12.5 meters. Okay, so this is basically positive, because you know the track was actually moving to the right. So the distance that it's covering, the displacement is actually positive. In a similar way, we can say for the car, the distance that was covered by the car, we can also say half. If you look carefully at that graph for the car, the base is 3.5 seconds. And then the height, it is about minus 15. Look at it carefully, it's in the minus. So minus 15, if you multiply that one, use your calculator, you find that it's about minus 26.25 meters. So this will be negative because, as you can see, the car is actually moving to the left. So the displacement that is making is 25. All right, so now if we do this, then we can actually be able to find the final position of the track. You see, the final position will just basically be, let me go to this, you see this, the 12.5 that we have found is the distance that it has covered while stopping. So in short, we are saying that the track is initially here, and then it starts applying the brakes. Then it covers a certain distance before it stops. So in order for us to find its final position, we just have to add its initial position plus the distance that it has covered. So basically we are saying that the final position of the track will just be equal to the initial position of the track plus the distance that this track has covered while stopping. Okay, the distance that this track has covered, just to make sure that you guys have understood, I'll go back to the diagram. So the track is initially at this position. While braking, it covers a distance that we have already computed, about 12.5. So in order for us to find its new position, we must add its initial position and the distance that it has actually covered. Okay, so we do this, that we have this equation, and I'm going to number this equation as my equation 2. If you look at it, this equation, I think I already have the number here. I have the value of this. If you go and check, it is about minus 35. And then I also have this, which is about 12.5. But for now, I'll not put those numbers there because I want to do it the physicist way. And in a similar way, so this is the final position for the track. I must just emphasize that this is the final position Okay, so this is the final position of the track. Similarly, for the car, the final position of the car will just be equal to its initial position plus this the distance that it has covered while stopping. So I'll say that this is my equation 3. This is my equation 3. And so how am I going to find the separation? Remember separation? After the two vehicles have stopped, remember the separation is given by this equation, equation 1. So separation, I'm saying that from equation 1, So from equation 1, I know that the separation delta x will just be equal to the final position of the car minus the final position of the truck. If you see this final position of the car is given by equation 3, this final position of the truck is given by equation 2. So if I substitute, instead of writing this, I write that. Instead of writing this xc, I can write that. Instead of writing this xt, I can write that. If I do that substitution, then I get delta x will just be equal to, remember delta x is the separation distance that I'm looking for. It will just be equal to this xc, which is that, plus delta xc, and then minus everything that is here, here, which is x naught t plus delta x t. And if you expand, if you distribute this negative here, then what you just get is x naught t plus that minus x naught t minus delta x t. Okay, so ladies and gentlemen, this what I have here basically is my symbolic answer. Okay, so this delta x t, you can see, I think we had already calculated it, and the value is given here 12.5. So what you just need to do now is you have already found a symbolic answer here. So you just now put in these values. You just plug in these values here, and then you are good to go. You find the answer. Okay, so let me just try to, just for the sake of completion, I know that you guys can do this. Just for the sake of completion, you must make sure that you are very careful with these signs, because I think this is a potential source of error. So you're saying that plus, the other one is minus 26.25 meters. The other one is minus, this minus that is here. But then the x naught t, it has a minus, so I'll say minus 35 meters. Of course, you can see this minus and minus. Eventually, it will give us a plus. Then I'll say plus, and then, well, I'll say minus, the minus that is here. So I'll say minus 12.5 meters. So we are now just plugging in the values which everyone else can do. So if you compute this using your calculator, then you'll be able to find this. You'll be able to find the separation distance, which is your answer, which I know. So the only thing that I want you to be careful with, very careful with, is just this. You'll see that this will give you a positive. Of course, this will give you a negative. And then there you go. You find then the units are also consistent. The units are also consistent. So I think I'll leave it here. I'll leave this question here, because I know that you guys can actually compute this using the calculator, and then you actually find the answer. All right, so ladies and gentlemen, for today, we are going to end here. At least I've helped you to solve these two problems, just to set you up and to see how we solve problems in physics. The emphasis here is that don't rush into putting the numbers. Okay, don't rush into putting the numbers. The coordinate system is extremely important when solving physics problems. So a diagram will indicate a very, very simple diagram indicating the situation at play will go a long way in helping you visualize the problem and subsequently be able to solve it. So thank you very much, and all the best as you do the other problems in the tutorial sheet. Thank you.